Welcome to the Chapter 4 video for the E111 lecture series. In this chapter, we're going to be talking about some more advanced techniques for solving complex circuits. We're going to talk in this first set of videos about the node voltage technique, then later the mesh current technique, and then later on in Chapter 4, we're going to talk about other things like superposition and equivalent circuits. Before we start looking at more complicated circuits, more complex circuits, it's important to clarify a few things about terminology and about just sort of general concepts with complex circuits. One concept is planar versus non-planar. So a planar circuit is a circuit that can be represented or is represented in a two-dimensional plane. That is to say, any wires that are shown crossing over one another are actually connected to one another. Non-planar circuits are ones where you kind of have to imagine the circuit wrapping in two dimensions. So you have to imagine a portion of the circuit resting in front of or behind another portion of the circuit. You can see in these two circuits here, this top circuit, connections are shown with a node, a little dot. They're I shouldn't say node. They're shown with a dot. A dot kind of shows a connection of three or more components. And you'll notice, in particular, there's no dot here at this crossing. And that indicates that there's no actual electrical connection here. And that means that this circuit is kind of folded in on itself. So the circuit's kind of shown with a wire crossing another wire that's not actually connected, which is sort of crossing over or crossing under, or however you want to think about it. And that wire can be redrawn as shown down below. It can be sort of pulled off the circuit and folded over to make a planar version of the circuit. But it's important to point out this planar versus non-planar. Sometimes you will encounter different techniques that are used to show a connection versus not a connection. The dot is a common one, putting a dot at a location where there's an actual electrical connection. Sometimes what people will do also is if there's ever not an electrical connection, they will draw the wire and kind of make a little jump. So it's quite common to see that, a little sort of bump where two wires cross to indicate that there's no actual electrical connection there. Another thing I want to talk about briefly is subscript notation. So we may have used this a little bit in the past, and we may have kind of glossed over it and not really talked about it. But it's important right now when we talk about voltages to talk about how we describe voltages using subscript notation. So the idea of subscript notation is when you have a labeled voltage, you have subscripts after it, one or two, which give you the reference or orientation of that voltage variable. So for instance, let's say I had labeled these A, B, and C on this circuit. Now, if I had used the symbol V, B, C, by the double subscript notation, that would indicate that this is the voltage. It is the voltage that is defined by taking the electrical potential at B and subtracting the electrical potential at C. Another way to think about that is, this is the voltage you would measure if you connected the positive probe of a voltmeter to node B and the negative probe of a voltmeter to node C. So essentially VBC, as shown here, that would be this voltage across R3 as labeled. And we can do other things. We can write a voltage label in any arbitrary collection of things. Let's say we had done VCA. VCA, that would be the potential difference between here and here. And one thing to note is when you have one of these strange kind of voltage labels where we're saying what's the voltage across this collection, this arbitrary collection of resistors, as noted by the labels, the node labels C and A or B or whatever. One of the best ways to find this voltage, if you solve for a circuit, if you solve for unknowns in a circuit, is to just go from the positive terminal, go from the first terminal that is noted in the subscript, and then just go from this terminal to the one you're ending at and add up your voltage drops. So if I start at the positive oriented terminal and I say, all right, what's the voltage drop across this resistor? And then I say, all right, what's the voltage drop across this resistor? If I add up all these drops as I meander from C to A, in this case, because it was notation CA, then that voltage change I would get would be VCA. It would be that VCA. We also have single subscript notation. Anytime you see something like this, like if we had said VA in this circuit, well, one thing you know about voltage is always a potential difference between two locations. So you can't just say, what's the voltage at node A? Unless you have some common voltage reference that is implicitly the second reference point. And that's usually shown using something like a ground label or something like that. Sometimes it'll be, you know, sometimes it'll, whoa. Sometimes it'll be like a 0 volt label. Can't write today. And just, and that's basically just a way of saying, hey, this node is my reference. This is my reference. And anytime I refer to, you know, any other electrical potential, if I use a single subscript, I'm saying, what's the potential at that node relative to my reference node? What's the potential at that node relative to my ground node, if you want to call it that? Ground is kind of a strange term, though. It's kind of, there's, sometimes when people say ground, they literally mean earth ground. Sometimes when people say ground, they mean chassis ground. In this class, for the most part, ground simply means our 0 volt voltage reference. It's very similar to the concept of sea level. So also with gravitational potential, just like electrical potential, gravitational potential energy is always relative between 2 points. And a lot of times when you're talking about elevation, you have, you know, which is kind of this, you know, displacement or distance through a gravitational field, you kind of talk about, you might say, oh, the elevation at this point is 3,000 feet, or the elevation at this point is 1,200 meters, or the elevation at this point is, you know, -5 meters. What's the reference point for that when you talk about elevation? The reference point is usually sea level. So, you know, most of the time people choose for elevation on the Earth, they choose the level, the sea level, which I've never really fully understood how that works because the sea level is kind of different. I don't know, whatever. I'm not going to think about it too much. I'm not a geologist. Who studies sea level? I don't know. It's clearly not me. Clearly not me. But it's the same idea. It makes it easier to just have a common reference and just say everything is relative to this reference. And for the purposes of analysis in this chapter, it really makes it easy because in this chapter, we really want to be able to just say, what's the voltage of this node? We want to be able to treat a voltage as just a single variable, not this kind of two variable, it's this voltage relative to some other random point. We want to treat it kind of as a single variable rather than a vector, if that makes more sense. Okay, so hopefully this subscript notation, double subscript and single subscript makes a little bit of sense now. More background definitions, and you might have to come back to this slide, and I might have to come back to this slide, and I might refer to things not quite exactly the way they talk about it here. But let's just get some terminology out of the way. What's a node? A node is a point where 2 or more circuit elements join. So in this circuit, D would be a node. This thing labeled D would be a node because it's connecting R2 and R3. And, you know, sometimes people think node is, it has to be labeled with a dot. Sometimes it has to be, you know, some people think it's got to be, have a variable label. A node is really just a way to say it's a connection between 2 things. Okay. And an essential node, this is usually what gets dotted. So an essential node is a connection, and in this case, it's not true because we have a dot just between 2 things here. But an essential node is a connection where 3 or more circuit elements join. And if you remember back to when we talked about the definition of series, we said series was, things are in series if they share 2 terminals and there's nothing else connected. So basically, things are in series if they share a node that is not an essential node. An essential node, being 3 or more things joining together, is critically important because that is a node at which currents can change. That's a node at which the currents flowing in are not necessarily the same as the currents flowing out because you have 3 branches, at least 3 branches. So you could have current flowing into one that might be split across the other 2 or any other combination thereof. It's a place where currents change, basically. A path. A path is a trace adjoining circuit elements with no elements included more than once. So a path could be anything. A path could be this. A path could be this, right? I mean, you know, a path is just it's just a path. I'm not gonna, the more I talk about it, the more confusing it's gonna get. What's a branch? A branch is a path that connects 2 nodes. So you might think, well, what's the difference between, it's gotta connect 2 somethings. So yeah, usually though, it would just be, you'd have a label, you'd have an actual, yeah, you'd have some labels. I'm not sure, I don't want to talk about it anymore because it's weird. I mean, I don't fully understand it, so I don't know the distinction they're drawing here that well. So a branch is a path that connects two nodes. An essential branch is a path that connects two essential nodes without passing through an essential node. So an essential branch would be, well, okay, let's go back and talk about essential nodes. What's an essential node in this circuit? Let's just label them all. This is an essential node, and I always like to draw my nodes like this. I like to draw them as these weird kind of, you know, these shapes that I always like to have the node kind of dip down into the little connection it makes, because it makes it a little clearer to me, at least, where it's going. That's an essential node. Is this an essential node? No, because it only connects two things together, so that's not an essential node. This is an essential node, though. This is an essential node. Did we miss any? I think we got it. So these are all essential nodes. And let's see, going back to essential branch, an essential branch is a path that connects two essential nodes without passing through an essential node. So this would be, let's change color here. So this would be an essential branch. And this would be an essential branch. And this would be an essential branch. So these are paths that connect two essential nodes without passing through an essential node. So basically this would not be, oh, sorry. Oops. This would not be, if you could see that. Do that again. This would not be an essential branch, because even though it connects two essential nodes, it passed through another essential node there along the way. Okay, and a loop is any path whose last node is the same as the starting node. So that's fairly obvious. That's a loop. That's a loop. That's a loop. All loops. Okay. And a mesh is a loop that does not include any other loops. So this would be a mesh. This would be a mesh. So a mesh is basically like a minimum size loop. A loop that doesn't have any subloops is another way that people put it sometimes. Sometimes people actually call these essential meshes. So some people use mesh and loop interchangeably, and maybe I do sometimes too. But sometimes people say essential mesh to basically refer to what's being defined as a mesh here, which is essentially something that it's a loop that doesn't contain any subloops. And a planar circuit, we already talked about that, so let's not talk about that more. Okay, so let's take a complex circuit. And let's take this complex circuit here, and let's try to solve for all the unknowns in this circuit. Let's try to solve for all these unknown currents in this circuit using what we know. Okay, so how could we do that? So first of all, we've this pre-labeled for you. We have all the unknown currents in this circuit labeled. You might think, is there any other unknown currents that aren't labeled? Well, you might have said this, right? But that's not really unknown, because it's got a current supply there. So we know that current's I. Switch colors again here. So we have 6 unknown currents, and based on math classes you've taken, you probably know if you got 6 unknown variables, you're gonna have to find 6 linearly independent equations in order to solve those. So how are we gonna get those linearly independent equations? Well, Kirchhoff's current law, Kirchhoff's voltage law, Ohm's law. That's our toolkit right now. So let's do that. Let's do some Kirchhoff's voltage law. Now, I usually like to just do Kirchhoff's voltage law around paths that include values that have my unknowns going through it, right? So if I did go around this loop here, and I go around this here, and this here, that to me looks like those are 3 loops that would include all of my unknown currents. So they would touch essentially all of my unknown labeled currents if I go around these loops. Seems like a good way to get 3 equations. So let's write those equations. So let's start here, going around this loop, do a Kirchhoff's voltage law. I like to add the sum of the voltage drops. So going around that loop, we'd have negative V1 plus, what's the voltage drop in this direction? Well, the voltage drop, which I just labeled on that resistor, because the current is shown entering the labeled positive terminal, that's going to be I1R1, right, by Ohm's law. And we could have labeled that variable an unknown voltage and then said that unknown voltage is it, but I'm trying to keep my variables to a little bit of a minimum here. What about this one? What about as we keep going around this loop? What's this voltage drop? Well, labeled currents entering the positive terminal, so it's V equals IR, so it's going to be I2 R5 and R3. Again, lucky us, current is shown entering the positively labeled terminal, and I'm just labeling the voltages as whatever I need to be a drop. So I just picked the plus and minus side because I'm looking for that plus and minus side, and then I'm picking the version of Ohm's law accordingly. So I'm going to erase all that and write it again. So that's going to be I3 R3, and then on R2 we're going to have I3 R2, and this all equals 0. We got back to our starting point. By Kirchhoff's voltage law, the sum total of voltage drops around that loop is going to be a big goose egg. All right, now took one out. Okay, now let's go around this loop down here. So going around this, we're going to start in this direction, go around the loop. So I got negative V2 plus. So when we get to this R2, I'm saying, what's this voltage drop across R2? Well, we got to be careful because now labeled I3 is entering the negative terminal of this. So we're going to have to use V equals negative IR. So this voltage drop, and I just put the plus and minus because that's the drop direction. I could have kept the old labeled plus and minus, and then just would have been an increase. So we would have had to subtract the increase. So we would have gotten the same thing. So we're going to have negative I3 R2. And there's another way you can think about this. I3 is the current flowing this way. Negative I3 is the current flowing this way. And we need the current flowing this way times the resistance to get the drop across the resistor. So lots of ways you can think about this if you want. Whatever it takes, just don't mix it up. You will. Everybody mix it up. I mix it up. People mix it up. It's fine. I mean, it's not fine, but it's a mistake that you make and you learn from. And then you make it less often, and then hopefully someday when you're teaching the class, you don't make it live on the internet, hopefully. And then we got another drop. The drop here is going to be the current entering the label negative, so it's going to be negative I3 R3. And look at this, right? We had positive here, negative, and negative. We had the negative versions of these equations when we went down the second loop. Why is that? Because the first loop we were going in this direction, and the second loop we were going in this direction. So as we're going around this second loop, we're doing the drop this way, and as we were going around this top loop, we were doing the drop this way. So we got the negative. Anyway, all right. Let's finish this up. I got to stop talking and actually write this. So now we got R6. Luckily, we got direction on our side now. So now we got I4 times R6, and then we got plus I5 R4 equals 0. Okay, lastly, let's go around this other little loop around here. Starting here, working my way around. So I want this drop, and I want this drop, and I want this drop. So we got negative I4 R6 plus negative I2 R5 plus I6 R7 equals 0. Okay, that's 3. 3 equations, 3 unknowns. 3 equations, 6 unknowns. I need 3 more equations. How do I get those other 3 equations? Well, I got 3 using Kirchhoff's voltage law, so let's go for 3 using Kirchhoff's current law. Clean this up a little bit. Okay, so where are we going to do the Kirchhoff's current law? Let's do it at a place where we have lots of these current connections. So let's do it here. Maybe here. We could also do it here, I suppose. I don't know. We're just stumbling our way. This is all we know. We haven't learned a technique yet, so we're just doing it wherever. Let's start up at B just for fun. I'm going to write the sum of the currents flowing out is equal to 0. And we got to be careful because B, this node B is actually this whole thing. Node B is this whole wire, right? This is all wire. It's just wire. So if we're writing the currents flowing out of this node, we got to write the currents flowing out of the whole thing here. So what do we got? Up on top, that current flowing to the left is negative I1, right? Because I1 was flowing in, but I'm just for consistency writing the sum of the currents flowing out is equal to 0. I1 was shown labeled flowing in, so it's negative I1. The current flowing down to the on the left is I2. Then we got I6. And then we got, what's this current here? What's that current? Well, that current is the opposite direction of I, so it's going to be negative I. All that equals 0. Now let's go to C here. Let's go to C. All right, so the current's flowing, the sum of these currents has to equal 0. And what are my currents here? We got I1 plus negative I3 plus negative I5 equals 0. And let's do E now. I got, so current's flowing out, so that's negative I2, that's I3, that's I4. So I got negative I2 plus I3 plus I4 equals 0. Okay. Now, could I do G? Could I do G? I could. So the current's flowing out of G. We got I5 plus negative I4 plus negative I6 plus I equals 0. Now we're good. We got 7 equations and 6 unknowns. But it turns out that if we have 1, 2, 3, 4 of these Kirchhoff's current law equations, one of them is not linearly independent. How do I know that? Because I'm just telling you that one of these is not linearly independent. One of these is going to be useless for the purpose of solving. It's fine. We got 6, but we don't need all of these. We only needed the first 6. How did I know that we only needed sort of these first 3? I mean, any of these 3 would have worked. How do I know that? I don't know. How do I know that these equations are linearly independent? I mean, I'd have to do the math. I'd have to actually go through the process of checking it. If I was doing this the traditional way, I'm telling you right now that these are 7 equations. One of them is not linearly independent. One of these current equations is not linearly independent. But how do we know? It's tough. We didn't really. You know, if we're doing this the hard way, we're just writing equations, and then we got to do the real math of checking for linear independence, solving this matrix, you know, reducing the matrix, all that kind of mess that we have to go through. We can do this though. Any complexity circuit, we can do this. It's an option, but it is a lot of work, and it's a lot of just raw math, and there's got to be a better way. So we got my boy Ron Popeil here, and then the new ones. If you're too young, you probably don't remember this guy, but I think he sold my family a lot of food dehydrators and fishing poles and stuff like that. Yeah. Anyway, there's got to be a better way, right? This is what life is. Life is you do something till it gets too complex, and then you develop a new tool to make it easier, or you buy a new dehydrator or new ShamWow or OxyClean or whatever, right? You always, when things get too tough, you find a way to make it easier on yourself. And that's what chapter 4 is. Chapter 4 is we can do this. We have all the tools technically to do this. And if we're a computer program, that's probably how we do it. We might actually, you know, solve unknowns in a circuit by just taking every node, right, and generating the equation, every loop, right, generating the equation, and then a computer might not care about six simultaneous equations, solving them. I do. I can't. If I try to solve 6 simultaneous equations on paper, the odds of that working out correct are maybe 15%, maybe 15%. And you all took math classes. You know what I'm talking about. When you get up to a certain level of equations, your chance of making just one of those little tiny silly errors is very high. So let's make it easier on ourselves. So the first way of making it easier on ourselves is the node voltage technique. Now these are techniques. These are actual processes that you can follow, where if you follow these techniques, you are able to follow a step-by-step process, and it will guarantee you a minimum effort way of finding unknowns in a system. Okay. So the node voltage techniques works as follows. It's a way of solving for all the essential nodes in a circuit. So all the essential node voltages in the circuit. So let's take this, and based on our definition of essential node, let's label our essential nodes in this circuit. And again, I have a weird way of labeling my essential nodes. I like to make them do these just so I make sure I don't miss a connection to the node. We have 3 essential nodes in this circuit. Now you might say, what about this? That is not an essential node. That is a node, but it only connects 2 things. It connects the 10-volt supply and the 1 ohm resistor. It doesn't connect anything more than that. And basically the way node voltage works is once you use this technique to solve for all the voltages at these essential nodes, once you know that, you can find anything else in the circuit fairly easily. So once you know all of these core sort of fundamental voltages around your system, finding the other stuff is kind of like little, maybe a little KVL, KCL, maybe a little Ohm's law, a little power equation, something, right? It's not too much work after that. And the idea here is this minimizes unknown variables. So this technique, all the techniques that we do, is minimizing the number of unknowns, makes the math easier, makes the process easier, makes it more likely you can do this by hand on paper and not have to use a matrix or use other, more complicated software. And the most important thing, if you follow the technique, it guarantees you a set of linearly independent equations to solve. So you don't have to go through that test of linear dependency. Anyway, you don't have to go through that. If you follow the process, you're going to have the equations you need to find your unknown. Let's do it. I'm just going to jump in. I'm going to tell you the steps, and then we're just going to start doing it. So step 1 is label all the essential nodes in your circuit. Well, we already did that in the previous image, but let's do it again. Never hurts. Now, I'm going to tell you something right now. You know those little like pens where like if you can like click the little things on top and it changes the color of the pen? It's got like little 4 clickers, or like if your family's rich, it's got like 20 clickers on there. Well, those pens actually come in really handy if you're working on paper in this class. So like when you're doing homework for this class, for chapter 4, I really like those pens because you're going to be writing a lot of junk on your circuits. And you're going to see, I'm going to be writing a lot of junk in what I do online. And having the ability to change color, to like label one node in one color, one in another, it really makes it easier to see visually what's going on in the circuit. It makes you less likely to make a mistake. So if you ever needed an excuse to go get one of those cool pens, if it was always just vanity, if it was always just, look how much money I got 50 colors on this pen, now you actually have a reason to get it. So you can spring for the $3 or whatever those things cost, get one of those pens. They're great. They actually are helpful. You'll also use them when you do digital circuits later on, but they work in this class very well. They're very handy. Okay, so you have my permission. If you're trying to get somebody else to buy you that pen and you're like, no, I need it for school, then you can show them this video. You can show them me saying they need one of those clicky pens, at least 20 colors on that sucker, at least. They need it for school. It's essential. Okay. Speaking of essential. Okay, so the cool thing about node voltage is we get to pick one of these nodes to be our reference node. So remember we talked about single subscript notation, double notation. So we get to pick one. One of these nodes, we get to say, this is my 0-volt node. We get to say, this is my C level. This is my reference from which all my other voltages are referred. Because if we take a circuit and we increase the voltage of the entire circuit, doesn't matter. What matters in circuits is the relative voltage between things. Like my cell phone or my calculator. If I have my calculator here, this thing's powered by, oh, you can't see it. The video's dying on us. But this thing is powered by 3 batteries. I got 4.5 volts. And within the circuit, there's something between 0 and 4.5 volts across these nodes relative to the negative terminal of the battery. But if I take this calculator and I put it in my pocket and I'm wearing wool socks and I go shuffling my feet on carpet, guess what? I have stripped I have raised my electrical potential of my body and this calculator thousands of volts. I mean, we've probably really increased our electrical potential relative to the planet Earth. We're probably, I mean, we can easily be up in 1,000-volt range. And yet my calculator still works. How does a calculator still work if it's up at 1,000 volts? Well, it doesn't matter what voltage it's at. It matters what the relative voltages are in its circuit. That's what actually does work. That's what actually makes things chooch. That's what actually makes the electrons do their thing. So it's all relative. And so if it's all relative, guess what? We get to pick a reference. We get to pick a zero. So we can pick a zero node. And it doesn't mean that zeros are lowest. We might end up solving for a node and the voltage of that node is negative 12 volts relative to our zero volt reference, but we get to pick a reference. And the cool thing is when we pick a reference, we know the voltage of that node. So like right here, I'm just gonna call this 0 volts. I know the voltage of that node now, it's 0 volts, but that doesn't matter, right? What matters is what the relative voltage is at all the other nodes there. Okay. So I picked and now I got to label all the remaining essential nodes. So I'm going to label this one V1 and this one V2. Does it matter what I called these? No, just something that I can remember, something that I can, that's clear to me, something that's clear to label. So don't label them I or something. Don't label them R, pick a label that's not going to mess you up when you're doing the math. But other than that, it doesn't matter what you name them. You can name them. Oh, something. I'm getting way off, and if you can skip through this if you don't like the tangents that I go on. But I saw something one time that said it showed like this shape, right? It was like this shape, and then it was like, and it said one of these shapes is named Bob, and one of these shapes is named Kiki. Which shape is named Bob and which shape is named Kiki? That's all I did. I just showed you two shapes. One of them's named Kiki, one of them's named Bob. And it's like 95% of people name this one Kiki. And like 95% name this one Bob. And that's weird. I don't know. It's like the sound, like our bodies, our brains kind of into, I don't know if it's from like the softness of how our mouth moves when we speak it or whatever, but we just know one of them's Kiki, one of them's Bob. They're just abstract shapes. One of them's Kiki, one of them is weird. I don't know. It's strange. Maybe in your head, maybe you thought this one was Bob and you're the 5% or whatever. But anyway, that's weird. I'm just talking about naming things here, but that's fascinating to me. That happens. Okay. So we named them. So step 3, we got a checklist now. You're probably dying for a checklist after chapter 3. You're probably just can't wait to actually have a process to follow. So step 4, write the KCL equation at each labeled node. So basically at each labeled node, so that being the reference doesn't count as a labeled node, the ones we just gave names to. So what does that mean? So KCL at these nodes means that we're going to write the equation for this plus this plus this equals 0. And this plus this plus this equals 0. That's what writing the KCL equation is going to mean. And then lastly, we're going to solve the equations to find the unknown node voltages. And then the book adds another step. I think the book calls it step 6, but that's basically, find the little stuff. So for instance, if I needed to find, the current through this 10-volt supply. Well, I don't know that directly from these node voltages. I don't know any currents technically, but I can find all my currents using Ohm's law or something. There's some way I can find all my unknowns in the circuit after I know the node voltages. So let's do it. Let's follow this process for this circuit. And I'm going to warn you ahead of time, the math isn't super clean, but we're just going to go through this. I think this is the last. Yeah, we're just going to go through this whole thing. So we had already, we had called this one 0 volts. And remember, this is the whole bottom here is that 0 volts. We call this one V1, and we call this one V2. I like the blue right now. I'm going to stick with the blue. Okay, so we had labeled our essential. I'm going to skip the labeling because it's going to mess it up. I'm just going to want to erase it afterwards. We named them, picked a 0 volt reference. Now, let's write these equations. So let's write the sum of the currents flowing out of that node 0. The sum of the currents flowing out of here is 0. And the key is we want to write these equations, these Kirchhoff's current law equations, using our unknown voltages, V1 and V2. So we want to use, these are the only variables we want to use when writing this equation. So let's do it. Now, this is really important to pay attention to because we're going to kind of start to play a little weird with voltage. We're going to start to kind of sort of play a little loose with how we use voltage here. But if I'm looking at the current flowing this way, that's the current through the 1 ohm resistor. What is the current through that 1 ohm resistor? Well, by Ohm's law, we know that it's going to be, the current through it is going to be the voltage oriented like this times the resistance. So what is the voltage oriented like that? Well, the voltage oriented like this is going to be the potential on this side minus the potential on this side. That's going to be that voltage. So what is that here? Well, the voltage on one side, the voltage on this side is V1. What's the voltage over here? It's a little weird. We have a 10 volt supply. I don't immediately think it's 10 volts, but basically the voltage on that side is going to be whatever voltage this is plus 10 volts, right? I'm just messing everything up. So if we had 0 volts here, 0 volts down here, we went up 10 volts, that means the potential here is 10 volts. So it's going to be V1 minus 10, and that is going to represent this voltage across my 1 ohm resistor divided by 1, and that's going to be the actual current flowing to the left there. That's the current flowing to the left. What's the current flowing down here? Try to write the equation for the current flowing down there yourself. This is a good time to pause it. Try to be honest with yourself. Try to say, what would the equation be for this current flowing down through the 5 ohm resistor? Okay, hopefully you did that. Hopefully you paused it. Maybe you didn't. So again, the current flowing down this way is going to be the potential on this side minus the potential on this side divided by 5. So it's going to be that voltage, the potential across that resistor in that orientation divided by 5. The voltage on this side is V1. The voltage on the other side is just 0. And then lastly, we have this current to the right. That's going to be the voltage on this side, which is V1, minus the voltage on this side, which is V2. Now, it should be noted, what happened here is, because I was consistent about writing the voltages flowing out of this node, look what happened to my equation. My equation was V1 minus. It was V1 minus. It was V1 minus. It was V1 minus written every single time as I was writing the currents flowing out, because the currents flowing out through some resistor is always going to be the potential on that node side minus the potential on the other node side. That's going to be the orientation of voltage that gives us, by Ohm's law, the current flowing away from the node through that resistor. Okay. Second equation, V2. Try to write the whole V2 equation on your own. Pause it. Try to write that mesh current, sorry, that node, sorry, that Kirchhoff's current law equation at V2 on your own. All right, now let's do it. So I'm just going to start with the current to the left. Doesn't matter which we start with. We can start in any order. The current to the left, that's going to be the voltage on this side minus the voltage. I'm going to switch colors here. That's going to be the voltage on this side minus the voltage on this side divided by 2 ohms. That's going to be V2 minus V1 divided by 2. Now again, I am now writing the equation at V2, and I'm starting to write V2 minus, V2 minus, V2 minus. This is a trend you'll start to see if you're consistent about writing the currents flowing out of the node. This is one of the reasons why I like to tell people, stick with the one method, so then you start to get consistency, you start to be less likely to make errors. The current flowing down here is going to be V2 minus 0 over 10. I'm just going to write that as V2 divided by 10. And then the current flowing to the right here. What's this current flowing to the right? Well, the current flowing in this way is 2 amps, which means the current flowing the other way is going to be negative 2 amps. And that equals 0. So I'm actually kind of done. I mean, as far as for this class, we have 2 equations with 2 unknowns. So what if you're able to do this, that's the process I want you to learn. The rest of this is the stuff that your math teacher hopes that you, if you pass their math class, hopefully you're able to simplify these equations right now. I always hated though when I took a class and they just said, "Oh, now it's just equation simplified." I always liked, you know, there's a lot of distance between you and algebra sometimes. So it's always good to see refreshers again. And honestly, lots of people have different techniques for simplifying equations. And my techniques are weird. People have told me my techniques are weird, but you're going to get to see the way I do it and the way I think about it when I'm simplifying these. So, let's just do it. Let's just go through all the algebra, at least a couple times. We'll go through the whole algebra all the way and see what happens. But I'm warning you, this one I know doesn't come out clean. So I hate fractions. We all hate fractions. So the first thing I do is I multiply these equations by whatever I need to get rid of the fractions. So I'm going to multiply this one by 10, and I'm going to multiply this one by 10. And then I'm going to rewrite these equations. So multiplying the top one by 10, I get V1 minus 100 plus 2. Oh, sorry, geez, 10. Oh, man, I'm almost messed up right off the bat. 10 V1 minus 100 plus 2 V1. And then, 0 over 5 is 0, so we're going to skip that. Plus 5 V1 minus 5 V2 equals 0. You say, John, where did the 5 come from? That was 10. Remember, we're multiplying this whole thing through by 10. So 10 divided by 2 was 5. That's where the 5 came from. Okay, second one. We're also multiplying the second equation by 10. So we're going to get 5V2 minus 5V1 plus V2 plus, this is going to be negative 20 equals 0. Okay. Now we got to solve for either V1 or V2. We got these a little bit, let's condense these a little more. Worried about running out of room. So let's condense the top one. So total, I got 17 V1. And I got minus 5 V2. And flipping that 100 to the other side of the equation, I get positive 100. For this one, I got negative 5 V1. And then I got 6 V2. And flipping that negative 20 to the other side of the equation, I get 20. Okay, so now I think this is where my way of dealing with algebra gets different than some people's. So I want to get rid of the V2 here. And I got a negative 5 V2 in this equation. And I got a positive 6 V2 in this equation. So if I multiply this equation by 6, it's going to give me a negative 30 V2 here. And if I multiply this equation by 5, it's going to give me a positive 30. So if I have a negative 30 V2 and a positive 30, then I can just add these whole equations together and it should get rid of the V2. And that's the way my mind works. That's the way my mind wants to get rid of this V2. So let's do it. You know what? I'm controlling the presentation, so we're going to do it my way. I got to avoid my head here, make some space. I'm going to start working up here. Let's multiply that top equation by 6. 17 times 6 is, oh my gosh, working without a wire. It's a 60 plus a 42. So 102 V1 minus 30 V2 equals 600. Oops. And then multiplying the bottom equation by a 5, we have negative 25 V1 plus 30 V2 equals 100. And then for me, I'm just going to add these equations together. So I'm going to add them together and I'm going to get, it's an equality, right? You can add, both sides are equal. You can add, it's fine. So we're going to get, it's going to be 77 V1, and then these are 0 equals 700. So V1 equals 700 divided by 77. Yeah. 9.09 volts. Easy, right? Okay. So now that we got that, I just go back to my cleanest version of that I can plug this into. So I'm going to plug this V1 into, I don't know, probably here. So I'm gonna redo this equation a little bit, right? Let's do this the normal way you do it in algebra. So let's say, so this is 6V2 equals 5V1 plus 20 divided by 6 divided by 6. So V2 equals 5 times 9.09 plus 20 divided by 6. $10.909. Okay. So we know V2, 10.91-ish. And V1 is 9.09-ish. Okay, that's it. So we solve for these voltages. So what good are those? Let's put these back on here. 9.09, 10.91, and this was 0, right? That was our reference, is 0. Okay, so what good are these? What can we solve for now in this circuit? Pretty much anything. So let's say power developed by the 2 amp supply. Well, we know we got 10.91 volts across this 2 amp supply. So the 2 amp is shown entering the negative terminal. So the power is going to be negative I times V, negative 2 times 10.91, whatever, it's, negative 22-ish or so. Okay, we solve for the power for that. What else? What if we want to know the power dissipated by the 1 ohm resistor? All right. So then what's the voltage across this 1 ohm resistor? Well, if we know the voltage, we can do power is equal to V squared over R. So what's the voltage across this 1 ohm resistor? We actually already solved for the voltage across this 1 ohm resistor back here. Remember, this was the voltage across the 1 ohm resistor. We used it to find the current. So it's going to be 9.09 minus 10 squared divided by 1. That's going to be pretty dang close to 1. I don't want to calculate it out, but I'm just showing you. You can find all these unknowns. What about the current through the 2 ohm resistor? Let's find the current this way through the 2 ohm resistor. The current this way through the 2 ohm resistor is going to be 9.09, the voltage on this side of the resistor, minus the voltage on this side divided by 2. And these are weird, right? Again, I told you we kind of play a little fast and loose with voltage here, but that's one of the advantages of using this kind of relative notation for voltage. We can just say the voltage. Normally, I said you always say the voltage across two things. Well, now we're going to talk about the voltage at a location because implicitly it's relative to that 0 volt reference. So we are still talking about the voltage across the circuit between one node and our reference, but I'm just going to start talking about voltage as the voltage at the node because it makes it easier to think about it that way. Power developed by the 10 volt supply. Well, so now we just need to know what's the current. Well, we can do the current here. So if we find the current here, that's current entering the positive terminal, right? So if we find that current, power is equal to I times V. And that current, we know that current. Because again, we had solved for that current here. Oops. That current is 9.09 minus 10 divided by 1 times V, which is 10. So that's our power developed by the supply. It looks like it will be negative, so it will actually be power developed. So the point is, once we find these essential nodes, we can relatively straightforwardly solve it. Sometimes there's a little technique, sometimes there's a little practice, sometimes you got to think about how to go from those node voltages to your unknown value. But once we solve for these node voltages, it becomes a very simple and easy task of finding any other unknown in our circuit. And that's the power of the node voltage technique. And really, what's kind of a breath of fresh air about chapter 4, I understand this stuff is complex. I understand we just did, I mean, look at this. We just did this, right? We just destroyed a page here. But the nice thing is we followed a technique. We went step by step and we followed these steps. And by following the steps, we were able to get to a solution. And it's not just this creative, it's not just this, I don't know, let's throw equations at it till it sticks. It's a process we can follow. And it really makes the work we do easier. And it lets us do more complex circuits. And you'll see more complex circuits. But the advantage is it gives us a process and a technique. Okay, so next time, in the next lecture, we're going to talk more about the node voltage technique, and we're going to talk about we're going to make it a little bit more complex. We're going to say, what if we have a dependence applied? Not too scary. But we're also going to show some things that can pop up while you're doing node voltage analysis and how to handle those sort of strange things that can show up in a circuit. Okay, until next time, thank you.